tells in these things. So I'm going to be talking about random walks on networks. So just fix some infinite graph G and let xn be the simple random walk on G. And then dist will be the path distance between a pair of vertices in G. So it's an infinite connected graph. And then anomalous diffusion is this phenomenon that in sort of various graphs that have some, say, bottlenecks or defects or holes, then the speed of the random walk is less than diffusive. So by which I mean that after n steps, you tend to be closer to your starting point than square root of n. Okay, so everybody knows these things. And then you can ask, you know, what controls this exponent beta? So let me give some notions of dimension. I'm using names that come from the statistical physics literature, but okay. So first of all, this BG here is the graph ball of radius r around this vertex row. So and then these are going to be informal for a moment, but the fractal dimension here is the rate of volume growth of balls in the graph. The walk dimension is this exponent dw that describes the expected time for the random walk to exit a ball of radius r around its starting point. I'm going to say more about the resistance exponent as we go, but this describes the level of conductivity of the underlying material or substrate, the graph here. Yeah, so here's a picture of what I'm going to say formally what the effector resistance is in terms of harmonic functions in a moment, but basically if one induces a potential difference between the ball of radius r, think about the graph as an electrical network, induce a potential difference between the ball of radius r and say the complement of the 2r ball, or just the set of points at distance 2r, then this induces some current to flow in the graph, and the effective resistance is the inverse of that induced current. So the higher it is, the less conducting the underlying graph is. And then if you sort of, like, well, especially in statistical physics, if you think about this, this conductivity exponent or this resistance exponent as giving you, as describing sort of a material that's somewhat homogeneous, then if you harken back to, say, to Einstein's paper on Brownian motion, he derives there the rate of diffusion of charged particles, and what you get is an equation that looks like this, relating the walk dimension, the fractal dimension, and the resistance exponent. Okay, and just to be sort of okay, so yeah, so first of all, if one just considers ZD, then of course the walk exponent is 2. The standard random walk on ZD is diffusive. But the reason for that, I mean, you know, sort of if you look at this thing in D dimensions, this equation describes that because the growth dimension is the dimension D, and the resistance exponent in ZD is 2 minus D. So sort of basically I'm thinking about walk dimension 2 as sort of baseline diffusive behavior, and this interplay as kind of the Euclidean interplay between the growth and the resistance. And then when this interplay is altered, one gets sort of this kind of anomalous diffusion behavior. So just again for intuition, think about something like this is a graphical Sierpinski carpet. So when you remove a bunch of holes from the integer lattice, the fractal dimension d sub f increases, the resistance exponent increases, this becomes less conducting, but they don't do, but these two things don't, this increase and decrease don't cancel out. So for instance, in the Sierpinski carpet, one gets a value of the walk exponent that's bigger than 2. So diffusion is anomalous there. And then the question I'm going to address now in just a moment is sort of under what settings does this relation hold generally? And I'll motivate why you might care about that in particular for a seminar on random geometries. Okay, so let's just look at the, okay, so what happens in this is again going to be informal, but here's what I mean by random media. So the basic setup is going to be that there's a random rooted network with conductances on the edges. These conductances, right, if you take this simple random walk where the probability of a step is proportional to the conductance along that edge, yeah, the conductances induce a random walk on the graph. And then the major assumption I'm going to be making that sort of is different from previous work, at least previous work on sort of establishing such a relationship in general, is that the random network is reversible. Okay, so if I look at the graph and the starting point of the walk, basically, yeah, if I look at the graph and then sample a random edge by choosing the root and then taking a random step, this should have the same laws if I reverse the order. And let me just say that in for the setting I'm considering right now, this is equivalent to okay, under some mild assumption on the conductances, so that everything makes sense. This is equivalent to just saying that that the network, that G comma x0 and G comma x1 have the same law. Okay, so it's just saying that sort of that we're in a stationary random environment. And then the theorem that I'm going to prove, this is an informal statement, I'll take the formal version soon, is, oh, I see, I introduced one more. So first of all, that this Einstein relation holds, so if the growth dimension and the resistance exponent exist, and the resistance exponent is not negative, then the walk dimension, and I've seen that on this slide, I've just introduced the spectral dimension. So let me come back to it in a second. Then the walk dimension exists, and this Einstein relation holds. Okay, and moreover, if one defines the sort of the spectral dimension as the exponent governing the rate of decay of the return probabilities. So here, P sub t here is the transition function. It's the discrete time heat kernel. So this is the probability. So this P sub 2n rho comma rho is the probability of ending at rho after 2n steps if I begin the random walk at rho. The spectral dimension describes the rate of decay of this return probability. And yeah, so what we'll do is, yeah, the goal today is to verify these relationships under these sort of, basically in the setting of reversible random networks, which under this sort of polynomial growth assumption is equivalent to thinking about just stationary random networks. Okay, that's the informal statement of the theorem. So let me say why it's, sort of why having a theorem like this is interesting. One can look at a number of different random geometries. So for instance, critical percolation in high dimensional lattices, high here, meaning D sufficiently large. Then in that setting, sort of the Alexander-Orbach conjecture is that the spectral dimension, so this is, I just take a large critical percolation cluster in ZD for D sufficiently large. The Alexander-Orbach conjecture is that the spectral dimension should be 4/3. And then this was confirmed by Kozma Nachmias by establishing that the growth exponent is 2, the resistance exponent is 1, and then using a special case of this, basically using a special case of the verification of these relations by Barlow, Jirai, Kumagai, and Slade, it follows that the walk dimension is 3 and the spectral dimension is 4/3. So this is a situation in which sort of the spectral dimension was conjectured to be 4/3. It was conjectured to hold for all D, but experiments suggested for D small, it's not true. And then a verification of this proceeds by establishing control of the resistance exponent and the growth exponent, and then some yeah, and then verifying that that these relations hold. Okay, so that's one case where they were known to hold via previous work. The case of resistance exponent 1 is special. I'll come back later. Another example is, say, uniform infinite planar triangulation. So here the growth rate, sort of the fractal dimension is 4. The resistance exponent, essentially this follows from a sequence of known results, although it doesn't appear specifically. There is, I mean, in the paper, proved that it holds. So the resistance exponent is 0, and then this theorem I stated previously implies 2 known results, that the spectral dimension is 2. That was known earlier from work of myself and Gwynn and Miller, and also that the walk dimension is 4, which was proved a couple of years ago by Yuan and Tom. So again, this is sort of, these were proved in a somewhat more specific setting, and so, but the theorem I'll say today encompasses that setting. Maybe some evidence of that is that, well, I mean, the audience sort of knows well that there's sort of this more general class of random planar maps that can be coupled to mated CRTs, which then can be embedded into some variant of Louisville quantum gravity. And in that setting, the growth dimension is known to exist by work of Ding and Gwynn. Again, using this LQG theory, one can verify that the resistance exponent is 0. And so one gets, again, from these relations that in that setting, the walk exponent equals the fractal exponent, the growth exponent, and the spectral dimension is 2. So again, these were known from the same works as before. I just want to, so it's just, this is just a technical remark that the argument as sort of presented in the paper of Gwynn and Hutchcroft doesn't work for one sort of particular case there, this Schneider-Wood decorated triangulation. And I just want to point out that's because the argument uses stronger properties of these models than just the walk exponent and the growth exponent. And so the advantage here of having a general theorem, I mean, in particular, it also applies. Okay, someone is implying that I can't do addition. So let's see. That doesn't look interesting. Let's see, where did I mess up here? Yeah. This is, I think this is probably fixed later on, but let's correct it in real time. That might persist for some reason if I cut and paste it, but the correct relationship is that one, twice df over dw, and then the relation does hold. So thanks, Jacopo, for asking. No, it was definitely a typo. The spectral dimension, I'll sketch the proof of why that's true, and then we would have noticed that it was wrong. But it's df over dw, not the other way around. I'm positive that if I click once, it's going to go back, but we'll have to mentally correct it for now. But if we do that, then the relationship does in fact hold in this setting, right? 4/3, good. Yeah, so another example, actually, sort of where the consequence wasn't known, is this random walk driven by a 2-dimensional Gaussian field. So this is a model that was studied by Biskup, Ding, and Goswami, sort of kind of another discretization of the sort of, I don't know what another sort of, maybe another discrete surface type geometry that one could associate to the Gaussian free field. Here, the underlying graph is just the integer lattice, but the conductances are given by the exponential of the Gaussian free field with some exponent gamma. So this is a random walk that tends to walk towards places that the field is larger. And then in this case, the authors here prove that the growth dimension exists, the resistance exponent is 0, and they conjectured that actually the random walk should be subdiffusive, and the spectral dimension should be 2. And now sort of this, the theorem I'll state formally soon, verifies that that holds in this case. And then one more setting, again, one more setting where this is maybe a bit interesting. This is actually why I started thinking about whether this is true. Let's consider now two-dimensional critical percolation. So take bond percolation on an integer lattice with probability half. Take a large percolation cluster there. And I just wanted, so now the setup is a bit different. I'm taking the graph to be the integer lattice. So the metric is now that of the integer lattice, and I'm encoding the percolation in the conductance structure. So, so here, if an edge is open, I have its conductance being 1, otherwise its conductance is 0. Then in that setting, it's conjectured that sort of, basically for a conformal class of 2D lattice models, the growth dimension is 91/48. This comes from sort of, I mean, this was rigorously, this was rigorously verified in the case of the triangular lattice by Smirnov, and then the calculation from Lawler, Schrum, and Werner. And it's just I just want to point out here, okay, so it's not known that this resistance exponent exists in these models, but, sorry, interestingly, experimentally, it's easier. One can, with the same amount of computational effort, it's easier to estimate the resistance exponent. And so the sort of the estimates that are given in the statistical physics literature proceed by estimating zeta, then using this sort of prediction for the growth exponent to arrive at a prediction for the walk exponent. And so this theorem that I'll prove, it doesn't say anything unconditional because it's not known that zeta exists. But if zeta does exist, it justifies this estimation of the walk exponent from the resistance exponent. Okay, so that's the motivation. Now, okay, so what was known previously here? So there's a vast literature both for fixed graphs and for random graphs in what in what's called the strongly recurrent case, which is when this resistance exponent is positive. Here, there's many papers here. I've just thrown down a list of names, but let me mention the basic. Let me try to summarize basically what's known there, which is that if the resistance exponent is positive, and one makes a stronger form of this assumption on a resistance exponent, which is a pointwise upper bound on resistances in terms of the graph distance, then these relations hold. Okay, and just to state a version of that in the setting of random graphs, so that it compares to the setting I have in mind here. So there, one doesn't need sort of pairwise control on effective resistances, but you still need, and we'll see why this is the case in a moment. One still needs some sort of pointwise control, basically some control on that all of the effective resistances in a ball of radius r, there's a uniform bound on it, some kind of bound like this. So then, so under this assumption and zeta being positive, the relations are verified. And I just want to mention here that in this setup, there's no use of here I wrote unimodularity, but there's no use of reversibility. So there's no use of stationarity of the random environment for this kind of result. And the goal today is to do two things. First of all, to get rid of the need for a sort of some uniform pointwise bound on effective resistances, and to allow application to the case zeta equals 0, which is interesting because all of these, right? I mean, all of these random planar maps that can be coupled to a mated CRT have zeta equals 0. So to replace the assumption of zeta positive and this uniform sort of pointwise upper bound by stationarity of the underlying network. So okay. So let me see if there are any questions before move on. Okay, so yeah, the main tool here is, I mean, the main thing we need to be able to do is utilize this effective resistance exponent. So let me do a little bit of electrical network theory. For this, it suffices to consider a finite graph with conductances on the edges. One gets an associated reversible Markov chain with a sort of with the transition kernel that everyone expects. Right. So here's a picture of an electrical network. Let me remind everybody about at least one characterization of the effective resistance. If I take two nodes in the network and create a unit potential difference between them, this induces an electrical potential in the network. So if you don't want to think about these things in terms of electrical networks, you can just think about harmonic functions. This induces a potential in the network where, right, which with a defining feature, if we fix the boundary values, of course, everything is defined only up to an additive constant here. So if we fix the boundary values, then the potentials are harmonic on the graph minus the vertices A and B. Okay, so this is actually, yeah, okay, and then the connection between, okay, so the point is, yeah, you induce a potential difference between A and B. This induces potentials at all the other nodes. That potential is harmonic except for at A and B. So combined with the boundary values, it's the fact that H is connected means that that uniquely defines psi. And now what's going to be useful, at least for the next few slides, is to understand that harmonic function is basically the green function. So if one defines the green function like this, so this is, yeah, so this quantity, this is the number of visits start the walk at A. This is the number of visits the walk makes to X before it hits B. And then in order to make this harmonic, I've scaled by the conductance at A. So if I'm going to call this this is the green function killed upon the walk hitting B. One can check that this function is also harmonic, and therefore the potentials are actually given by the green function scaled by its value at A. Okay, so I can't. Okay, so right, so this will be important momentarily. And then the Dirichlet principle says that, so you can take this if you want as a definition of effective resistance, or you can take it as the inverse of the current induced in the network. The effective resistance is the inverse of the Dirichlet energy of this potential, where the Dirichlet energy is defined in the usual way. Okay, so, and then more generally, if we have two sets A and B in our graph, then the effective resistance between A and B can be defined or characterized, depending on where you start, as the inverse of the minimum energy function that's, say, equal to 1 on A and equal to 0 on B. And then, as before, this minimizer will be harmonic everywhere except for A and B. Okay, so, all right, so that's all the electrical network theory. Well, okay, there's going to be one more thing. So if one takes these things and plays around, you can get a characterization of the effective resistance between two sets in terms of return probabilities. So let me just say what this characterization is. So tau here, so tau B is the hitting time at B. Tau A plus here is the first return time to A. Okay, so I'm starting so this quantity is I'm starting the walk in the stationary measure on A, and then I look at the probability that I hit B before I return to A. So that's a probabilistic way of characterizing the effective resistance between the sets A and B, where this C sub A here, this is the total conductance in A. Okay, so yeah, so basically what I want to do is just give some heuristic for why this Einstein relation should hold. And to do that, I'm going to use this characterization of effective resistance between two sets in terms of, again, this is just for intuition or to guide us in what we should do. I'm going to use this characterization. So if we now apply this in the setting we were in previously. So let's take our set A to be the graph ball of radius r. Take our set B to be the complement of the 2r ball. Then what it says is that if we start from a random, if we start from from a random point chosen according to the stationary measure in A, then the probability that we hit B before returning to A, right? Returning to A here most of the time means just taking another step inside A because we start in A. Then that's given by the inverse of the conductance times the resistance between these two sets. And now if we use our assumptions, this total conductance of A, at least let's say that the graph doesn't have conductances on it for the sake of this, is proportional to the volume of this ball of radius r, and the effective resistance is given by the resistance exponent. So one gets this expression for the probability of the walk hitting B before it returns to A. So r to the minus df minus zeta, and sort of if one believes sort of that this heuristic describes sort of, right? So in some sense this can be okay. This is the motivation for why for this equality that the walk dimension equals this growth dimension plus the resistance, because it looks like we need if we're gonna, how long is it gonna take us to hit B, which means to exit the ball of radius 2r? Sort of we need about the inverse of this many experiments, which is r to the df plus zeta. So this is not some in any way a formal proof. It's just all right. Of course, it's not but this is at least why you sort of like why. Yeah, here I'm taking a probabilistic interpretation of this electrical quantity that could be used to predict this relationship that the walk dimension is equal to the growth dimension plus the resistance exponent. But you can see that there are a lot of okay. So what are the objections one might make? One serious objection here is that the walk exponent here I've defined in terms of, right, I start at some point and then I look at the probability of exiting the ball, and in this expression I'm starting from the stationary measure on the ball, which of course could be two different things. So it's somehow we need to, this will be an important point to somehow recover approximate sort of that the random walk somehow approximates the stationary measure in this ball. And let me just mention here for intuition that this is a setting where the recurrent case, say when zeta is greater than or equal to 0, and the transient case when zeta is negative, are very different. Right? It's going to turn out that in the recurrent case, let's say when the strongly recurrent case, when zeta is positive, sort of we get this uniformity just because the random walk tends to, before it ever exits the 2r ball, it tends to become, it tends to mix in some sense on the r ball, right? Because the walk is very slow, and sort of it spends a lot of time in the r ball, enough times that it visits everything. Whereas in the transient regime, the reason that sort of a random walk started at rho might be at some intermediate time at a roughly sort of uniformly random point in this ball is quite different, because here it's not the case that we just walk around so much in the ball that we tend to visit everything. It's just there. In order to verify that, one probably needs some kind of assumption on the geometry that it's sort of it's isotropic in some sense, where there's no particular direction that's preferred. There's no particular direction of exit that's preferred much more than some other one. Okay. All right. So that's some intuition. Let's okay, and let me just also give you, sort of let me give you also the intuition behind this relationship for the spectral dimension. That one is somewhat simpler, right? If after n steps, the walk dimension describes the mean displacement as being n to the 1 over dw. So then if the walk is roughly uniform on a ball of radius n to the 1 over dw around its starting point, then I mean, in particular, the measure at its starting point is going to be the inverse of the measure of this ball, which is the 1 over n to the df over dw. Right? This is a ball of radius. This is a ball of radius n to the 1 over dw, so it has n to the df over dw points. So okay, so that's just some intuition about why this should hold. And let me just mention that the intuition is just that the random walk should look something like this. And let me just mention that even under the assumptions we've made, in the regime where zeta is negative, this can fail. So there are reversible random planar graphs with polynomial growth, and where this equality is satisfied, but the spectral dimension is not what you would predict from this heuristic. That wasn't so clear to us, but it's true. Basically, yeah. As an example, if one starts with say a square and then replaces it by this sort of 12 topological squares, and then iterates this process over and over, let's say, and then takes the graph, which is you could take this graph, or you can take the tangency graph of this graph. Then this is a case where this characterization, this expected characterization of the spectral dimension fails. And the reason is that, well, in this case, instead of the random walk spreading out like on the left here, the empirical distribution looks tends to look something more like, okay, the distribution of the walk looks more like, it's not, it doesn't spread out uniformly on balls of radius r. So sort of this general fact that these two things hold in the zeta positive or zeta non-negative regime can fail miserably, even in 2 dimensions, even when everything is reversible, when zeta is negative. Okay. Okay, so now, so now I want to tell you something about the this one. Here it is correct. Okay. So sorry, at some point I started writing this ratio the correct way. So now, okay, I'm going to focus on, proving this. And to do that, let me first give a sketch of how, in the strongly recurrent case, the strongly recurrent theory gives this this Einstein relation, that dw is equal to df plus zeta. And okay, so here's how sort of the argument looks. One induces a unit potential difference between, say, some vertex rho and the complement of a 2r ball. This induces, as we said, an electrical potential, right? Which is, again, this is the unique harmonic function that's equal to 1 at rho and 0 at the boundary. And then this pointwise estimate on effector resistances makes it so that the potentials are it makes it so that the potentials are sort of, in some sense, concentric with the graph geometry. Right. This assumption and small calculation says that if I choose a small enough ball around rho, right, the potential at rho is 1, and then, but in this small ball, the potentials are at least 1/4. And as we said, the potentials are described by the green function. So if all the potentials in a ball of radius, say delta times r, delta is some constant, are at least 1/4, what it means is that for every such point in that small ball, the expected number of visits to that point of the random walk started at rho is at least 1/4 of the expected number of returns. This is just because the green function is the potential. And then this value, the sort of the expected number of returns to rho before we exit to our ball, this is precisely the effective resistance. There should be between rho and the complement, which by our assumptions is at least r to the zeta. So what it says is that, right, if you look at this argument, it says that for every point in this small ball, this delta r ball, I tend to visit it at least r to the zeta times before I exit the 2r ball. Okay, that's what I just said. And therefore, the expected exit time, right, there are, in this small ball, again, delta is a constant, there are about r to the df points. I expect to visit them all at least r to the zeta times. Therefore, I need, before I exit the 2r ball, therefore I need at least this many time steps to make that, a realistic possibility, right? In order to visit every point in this delta r ball, r to the zeta times, I need at least r to the df plus zeta time steps. And that gives us this lower bound on the walk dimension, right? It says that it tells us that the walk doesn't escape from the ball too fast. And I'll just say that in the strongly recurrent case, like, this is the hard part of the inequality. The other side of the bound is just, take rho and fix at any point here, then this effective resistance bound will give you an upper bound on the commute time by standard arguments. This is the hard part of the argument. And I want to stress here that sort of this middle point, this middle point here, which says that all the potentials in the small ball are at least 1/4. What this is using is the fact that by assumption, the effective resistance to the boundary of this 2r ball is r to the zeta. And if I choose this delta small enough, then because of this assumption, the effective resistance to all the points in a small ball is asymptotically smaller than it is to the boundary. So what it means is that this is what gives me the fact that basically I visit all the points in a small ball many times before I escape. And you can see, for instance, why this argument doesn't work for zeta equals 0, why it doesn't work in the recurrent case. And it's just because then there's no scaling to benefit from, right? The point is, here I've used the fact that I can choose delta to be some small number so that delta r to the zeta, there are implicit constants all over the place. So if I choose delta small enough, delta r to the zeta is much smaller than r to the zeta. I can only, I can only get this gap between the potentials to nearby points and the potentials to point at distance 2r if the effective resistances are scaling in some way. And when zeta equals 0, there's no scaling. It just says that, right, the analog of this upper bound when zeta is 0 is just that all the effective resistances are bounded. Okay, so this sort of argument is very much stylized to the strongly recurrent case. So now in the last 10 or 15 minutes, let me tell you, so I just want to stress that the difficult part of extending this argument to zeta equals 0 and not having point-wise upper bounds is this part of the proof, that the walk it's this subdiffusive estimate, that the walk doesn't move very fast. It's this lower bound on the walk dimension. Okay, so now I want to state a formal theorem, and so let's do that. Okay, so first of all, instead of talking about the size of balls, since I have conductances, I'm going to talk about their volume. So the volume of a ball here is just the sum of the conductances in the ball. And then, right, okay, I'm going to use this notation that the volume scales like r to the df plus little o of 1. What do I mean by that? I'm only going to state it once formally. I mean that almost surely over the choice of the random network, this limit exists and is equal to df. So, okay, so, for all of these, for all of these associated quantities, that's what this means. So there's nothing tricky going on here. This is the way you should define them, okay? Let me mention, I don't know, maybe this is too far afield, that, I've highlighted these exponents in green because in the paper, I use these exponents when there's no averaging at all. So since we're requiring that something should almost surely have a limit, we could get rid of expectations here and just say that almost surely the time to exit, choose the random network, the random rooted network, we could say that almost surely the time to exit the R ball scales like R to the dw, even without taking expectations over the walk. Just something about choose a random walk trajectory, almost surely as R goes to infinity, the time to exit scales like R to the dw. And the same thing for this, for this mean displacement. You can actually get rid of the expectation here. It doesn't, in the theorem I prove all of the exponents are equal, so the annealed version is equal to the quenched version in both cases. But I just wanted to point that out. So here, so I'm making assumptions that all of these things exist. Of course, if you don't assume they exist, there's a bunch of inequalities between them, between lim sups and lim infs. But let me now, so none of this was all of those things were ideal. Let me mention that my assumption on the existence of zeta being non-negative is a bit stronger than one would like. So here's the, okay, so this bottom inequality, this is exactly what one would like. I'm getting some subpolynomial, I'm allowing some subpolynomial error sort of in the radius here. But the upper bound I require is stronger than having an upper bound on this quantity. The upper bound is a upper bound on the resistance from rho to the boundary of the R ball. So two things. This quantity is not very nice because, well, if you look at it, this sort of this bottom quantity is, in some sense, you could say it's a nice quasi-conformally invariant quantity in the sense that it deals with two, you can think about it as dealing with two balls of radius about R within some other ball of radius about R. Whereas this thing, refers to a single vertex. So, okay, it's not as nice a quantity. And also, okay, so the assumption I'm going to make is that these two exponents are equal. And that assumption only makes sense in the regime where zeta is non-negative. They will not be equal. When zeta is negative, this effective resistance will, in general, will always be at least a constant because the degree of the root here is a constant. And so I can't get something that's going to 0 with infinity. Okay, so this is still weaker than having a pointwise assumption to every point in the complement of the R ball, but yeah, it's to be noted there. Okay, you can believe that. All right, so this is what I mean by assuming the exponents exist. So if I say assuming df exists, and then it means that this limit almost surely exists. Okay, so those are what I mean by the exponent existing. What are my assumptions on the network? They're very mild. The conductance at the root has to be almost surely positive. The expected inverse conductance has to be bounded. We're not going to see it in the time we have left, but this is, for those who know, this is so that we can employ the mass transport principle. This is also mild. The strong assumption here is that the network is reversible. And then there's one other sort of boundedness assumption we need, which is that the graph balls have sub-exponential growth, right? This is a weak assumption because we're assuming that the growth is polynomial. But if we allow arbitrary conductances, then I'm assuming that the growth of the conductances is polynomial. We still, and this is something about the growth of the cardinalities of balls. But it's sub-exponential growth, right? It just says that this is at most e to the r to the little o of 1. So it's also mild. Okay. Under those assumptions, so if the growth exponent exists and these two resistance exponents are equal, which in order for them to be equal, they have to be non-negative, then these other three exponents exist and the desired relations hold. Okay, so if we go back, this beta, here I'm measuring displacement of the walk in two different ways. one is the exit time, one is in terms of the maximal displacement squared. So the theorem says that dw is equal to df plus zeta, and also this other notion, right? This beta is equal to dw. These two notions coincide. We won't see it. This is actually important in the argument. Okay, what's the primary new inequality here? The primary new inequality holds for any zeta, not just zeta non-negative. And it's that under an assumption on the growth, an assumption on a lower bound on these resistance exponents, that we have an upper bound on the speed of the walk. Okay, so so yeah, I'm going to simplify here. Let's just simplify the assumption to effective distance between the R ball and the complement of the 2R ball. And then what this theorem encodes is just the following. We want to prove under these assumptions and the assumptions on a network I made earlier that the conductances are reasonable. Then the walk doesn't escape too fast. Basically, the expected maximal displacement of the walk is bounded by, here there's a square, but it's a stronger bound. But we need is the expected maximal displacement is bounded by n to the 1 over df plus zeta. Right? So that gives us a lower bound on beta, and you have to trust me. This is the non-trivial thing. In particular, this is the lower bound. The argument that I gave previously from the strongly recurrent setting that used potential theory, that argument can no longer be done under these weaker assumptions, and it's getting replaced by this inequality. Okay, so I think I don't remember. Do I have between 2 and 7 minutes? Shin, are you in? I can't. Okay.
Yeah.
Okay.
Yeah.
All right. So let me say how we're going to prove that. It's going to be by a change of metric. So what I mean by a change of metric here is I'm going to take some non-negative weighting of the edges of the graph, and I need this weighting to be compatible with the reversibility of the network. Okay, so I'm going to choose this weighting such that this, that these two things have the same law. But for the sake of, actually, you can think about this because it's how things are chosen. This just means that I need to choose the weighting independent of the root. So I'm gonna, so this, I need a random edge weighting where that depends only on the graph and not on the root of the graph. If I have that, then it ensures that since the graph is reversible, also the weight along with the graph is reversible. I'm going to let this dist omega denote the path metric in G under the edge weightings given by omega. And then here is the main tool. It's a very simple tool. It just says that if I take some weight that's reversible in this sense, meaning that or not meaning, but it suffices that the weight just depends on the graph and doesn't depend on the root. If that weight is in L2, in the sense that the expected weight squared on a random edge is bounded, then this is the tool we're going to use. Then we can bound the maximal displacement squared by something which is asymptotically linear. So since there's a square here, what this means is that, right, I'm basically saying that the walk in this new distance is at most diffusive. Again, up to this little O of 1 error. So this is a general fact that this holds under our assumptions on the network. So basically the only non-trivial one being that it has sub-exponential growth. This is proved using Markov type theory. I'm not going to go into it. Basically, since the balls have size which is sub-exponential, by, they can be, say, by Bourgain's embedding theorem, the metric restricted to those balls can be embedded into a Hilbert space with distortion that's subpolynomial in the radius. And so then you can use results about reversible random walks on subsets of points in Hilbert space, which have diffusive speed. So this is going to be our main tool. And now I can tell you what we want to do. Recall that what we want to do is prove this for the graph distance. We want a stronger bound than n. We want something, we want an exponent which is 2 over df plus zeta. so now you can see here's a natural approach. Let's find a weight that's bounded in L2 such that the weighted graph distance is bigger than the unweighted distance by this power. And then we can apply this theorem, which says that the walk goes at most diffusive in the weighted distance, but since the weighted distance is much bigger by a power than the graph distance, that tells us that in the graph distance, the walk is even slower. So sort of, so like if I take this theorem on faith that I've written here, then in order to achieve the goal we want, which is that the speed of the walk is bounded by what's written here, it suffices to find a weight where that's bounded in L2, but where the weighted distance is larger than the graph distance by this power. And again, I should say that the regime here is df plus zeta bigger than 2. So, so this is indeed larger. Yeah, and to do that, actually, it suffices just to focus on one scale. So to find for every fixed star a weight that's bounded in L2, now I want a uniform bound on the weight for every fixed star, and such that if the graph distance is at least r, then the weighted distance is at least r to this power bigger than 1. Okay, and just the intuition here, for instance, let's go to the Sierpinski carpet, is that, right? Of course, I could take the edge weight just to be identically 1. Then it's certainly, the expectation square is just 1 in that case. But then I would get that the speed of the walk is at most diffusive. It's at most, my mean displacement is at most square root of n. So in order to do better than that, I need to make a better choice of the weight. And you can see what you might do, for instance, in a setting like this. If I look here, for instance, I see that, all of the paths that come through here, have to use these edges, say. So I might like to put a larger weight on these edges and then put a smaller weight elsewhere so that I still maintain the fact that the 2 norm is bounded. Right, so this is the game to play now, that maybe I can make all distances larger without violating this 2 norm bound, by concentrating on places where the graph is putting large weight where the graph is thin, because lots of geodesics have to go through those edges. All right, so that's our goal. Okay, so this is the last slide, basically. Let's see how we can do it. Okay, so this is just an annulus in the graph. It's a little r annulus where little r is, say, r over 100. And now I'm going to put some edge weights on the edges in this annulus. Where are the weights going to come from? Well, I just take the electrical flow from r to 2r. So again, the unique harmonic function, that's 1 on the r ball and 0 outside the 2r ball. And now my weight is just going to be the absolute value of the potential difference along the edge. Okay, so again, yeah, you can take the electrical, basically the electrical potential is going to give me the edge weighting I want on this annulus. What property does this weighting have? Well, everything in the r ball has potential 1, and everything outside the 2r ball has potential 0. And therefore, if I weight the edges by this, then the distance between the r ball and the complement of the 2r ball is at least 1, because when I move along an edge, the weight is proportional to the decrease in the potential, and it has to decrease by at least 1. So I have a weight where I separate these things by 1. And what I know about that weight is that if I look at the Dirichlet energy, this is by the Dirichlet principle, then it's equal to the inverse of the effective resistance across this annuli. And then by assumption, that's r to the minus zeta. Okay, so yeah. So now, okay, remember I want to have that the expected squared weight of this is at most 1. So now I just want to, I've chosen this weight, but I want to normalize it so that I can expect this quantity to hold. So in other words, I put weights on the edges of this annulus. I want to normalize it so when I average over a random edge in this annulus, that the weight squared is 1. That's, that should be the correct weighting. And so if we do that, that corresponds to, well, we know that the sum of the weight squared is this, so we rescale by the energy, but we also need to rescale by the total conductance in the annulus. Okay, so basically, I'm going to rescale this weight that I chose before so that this is satisfied, so that the average if I choose a random point according to a random edge according to the walk measure on this annulus, that the average weight squared is 1, right? Because again, that's what I'm trying to achieve for this global weight. And if we do that, then this rescaling gives us that, right, in the unscaled weight, the distance across the annulus was at least 1. Now the distance across the annulus is at least r to some power. Okay, and now the major problem, that's actually what we wanted to achieve, except for the fact that this weight depends on the root. And I said that we had to choose the weight in a way that doesn't depend on the root. And so now that what you do is just sort of, tile the graph by many such annuli and just take this weight in every single one of them. And with the idea being that, if the root, say, happens to fall in the middle of one of those annuli, then every path from the root to the complement of its R ball will have to cross through, one of these annuli, and which means that the path has to pick up weight at least R to the df plus zeta over 2. So, basically I'm taking across a single annulus, and the electrical flow gives me a good weight that, it's the extremal length of the extremal width of the annulus that sort of stretches out this annulus by a power. And now, in order to stretch out all the distances by a power, I just tile with annuli. Of course, I might have missed where the root lies. So, if you're in a nice regular lattice, then you could just choose a small number of overlaps so that you cover everything with a bounded number of sort of tilings. And then in the general setting, you can just do something similar. Again, I want the weight not to depend on the root. So you can say, for instance, take some Poisson process of a fixed intensity, which for every vertex of the graphs will tend to capture it in one of these annuli. So basically, I construct a random weight by having a bunch of annuli appear where basically with some sort of, with a given intensity, and then just taking the sum of all the weights on the annuli. And this picture is more complicated, but what happens there is basically this one, that now wherever the root sits, it's going to be it's likely to be in the center of at least one of those annuli. And then for all the points outside the capital R ball, they have to cross through this annulus. And this annulus was weighted so that crossing through it requires this much distance. So in doing that, we achieved this goal that if the distances in the graph are at least R, then the weighted distances are bigger by a power. And from what I said before, using this tool, which says that the walk moves at most diffusively in the weighted distance, we get that it moves subdiffusively in the graph distance. Because again, the graph distance is smaller by a power than the weighted distance. Okay, so that was that's the difficult part of that's the difficult new part of the argument. Okay, so I'm going to go to open questions. Here are two natural open questions. So first of all, in this literature, say on strongly recurrent graphs, but also, okay, in this literature more generally, there's a way to nicely interpolate between sort of the bound on the spectral dimension and the escape time, which is describing the entire sort of decay of the entire heat kernel. At least in the setting where zeta is non-negative, it seems plausible that one can prove a bound like this. Okay, you have to modify this slightly in discrete time because, right, the walk can only go n steps in n time. So, but there is a formal, that you can add a restriction here so that this is a conceivable thing that could hold. So for instance, I asked UN about this. I don't know if it's true that, even in Uipt, I don't know if this holds. Although I suspect it should hold more generally. So this is the correct space-time scaling of the heat kernel in terms of these exponents. And it's a generalization of those two equalities we proved earlier. And then another fascinating thing is what happens for general zeta. So for instance, when zeta can be negative. And so here's a conjecture, which is an analog of this resistance conjecture of Grigoryan, Hu, and Lau. If we, in the zeta negative setting, we need to make a stronger assumption on the geometry. So just for lack of time, for those who know, if we assume that the graph satisfies a local Poincare inequality. Okay, so this says that that locally this bounds the severity of local bottlenecks in the graph in some sense. Then the question is, under this Poincare inequality, do we get a speed bound that looks like this? I just want to contrast this to what I just proved. So what I just proved is that holds, if you just look at the orange part of this thing, that the expected mean displacement squared is at most n to the 2 over d star. That's what we just proved. The requirement here is actually that this holds for all the possible starting points in a small ball around the root. So what I proved before is that it holds if you start at the root. Just using stationarity, you can get that. That means that this bound holds for 99% of starting points in the ball. But the extra thing here that one would need to get this entire theory to go through, also for general zeta, including zeta negative, is that that displacement upper bound holds for every starting point in a small ball around the root, which I don't know how to prove, but this Poincare inequality in particular tells you that, that maybe that there's no point inside a small ball that looks too bad, that looks spectrally too terrible from the perspective of the root, and therefore one might hope to prove something like this. I mean that would be amazing, because this conjecture is also open in the non-random setting. Yeah, but I think that would be really cool. I don't know how to do that. And then for those of you who study, who for instance, sort of understand well these mated CRT couplings and the geometry that one can get from the LQG embedding of a mated CRT, question 1 is also fascinating to me. So let me stop there and see if there are any questions.
Yeah, so feel free to unmute yourself and ask if you have a question. If not, then I can start out. So I have a quick question about this resistance conjecture. So you say that you prove this when x is just fixed to be the root.
Yeah.
But you prove that only for positive zeta, right? Or non-negative zeta?
No. This. Okay. I don't know. I'm going back because you wouldn't trust me. But no. This theorem, this one inequality holds for all zeta.
Oh,
so yeah, yeah. So this upper bound holds for every zeta. But what doesn't hold, or what I don't know to hold for every zeta, is this stronger bound. This stronger bound that holds for every point in a small ball around the root.
Right. So then, what is the input in the proof of the main theorem, which doesn't hold for negative zeta?
Yeah, it's the fact that that I was a little in defining the resistance exponent, right? There were these two exponents.
Right.
Yeah. So if so first of all, what doesn't hold in the general context is the other side of that inequality. So so the other side of this inequality doesn't necessarily hold when zeta is negative. And that's the other side, right? the point is that the other side of this inequality, which is basically says that you escape the R ball sufficiently fast. If you have a strong enough assumption on the effective resistance from the center to the boundary, that's an easy argument. That's like a standard argument. It's because you can bound the hitting time by the volume times the effective resistance. You can bound the hitting time from the center to the boundary by the volume times the effective resistance to the boundary. So if you have an upper bound on that, you get the reverse of this inequality. Sorry, when I say bound, you can upper bound it by that. So the reverse of this inequality follows almost immediately from an effective resistance bound from the center to the boundary. But if you only have an upper bound from the R ball to the complement of the 2R ball, well then that upper bound doesn't hold anymore. And if you want a pointwise bound on the effective resistance, it only holds when zeta is not. It can only possibly hold when zeta is non-negative. A different way of saying that is that the upper bound you get on the hitting time from the root to the boundary is actually an upper bound on the commute time from the root to the boundary and back to the root. And in the transient case, right, in the recurrent case, that's proportional to the hitting time to the boundary. Whereas in the transient case, when zeta is negative, it will take you like that. That upper bound is going to get dominated by the time it takes to get back to the root, which in the transient case may never happen.
Yep, I see.
Yeah. So, but basically, it's something about. Yeah, if you only have an effective resistance bound, upper bound from across the annulus, then it doesn't give you a bound on the speed. It doesn't give you an upper bound on how fast you escape the R ball. For that, it seems like you need something stronger. For instance, what would suffice there is say a Harnack inequality, like an elliptic Harnack inequality, which says that, say, harmonic functions on the R ball, are upper and, basically a harmonic function on the 2R ball. If you restrict it to the R ball, then its values are upper and lower bounded by a constant. If you make an assumption like that, then you can get this sort of proof to go through. In this resistance conjecture, if you like this, this conclusion actually would then implies, for instance, a Harnack inequality. Actually, this conclusion also implies that heat kernel bounds. This is a very strong conclusion. Sort of basically the entire theory there goes through if you have this sort of upper bound on the escape time. By the way, when I say Harnack inequality, there are these little O of ones everywhere. So you have to take everything with little O of one errors.
Yeah.
Can I ask a question?
Yeah.
Yeah, so my internet is pretty bad, but I will just try to make it clear. Suppose you focus on the Uipt case. Mm-hmm. So can you summarize what's the input you used, which are like well-known, and then what are the new results, just in the Uipt case? Yeah,
so in the Uipt case, there's no new result here. The assumptions are just the growth exponent, and then the strong assumption, which comes from the mated CRT and the LQG embedding, is that the effective resistance say across an annulus scales like polylogarithmically in the radius, and also the effective resistance from the center to the boundary so across an annulus, the effective resistance is at least an inverse polynomial in log R, and from the center to the boundary is at most a polynomial in log R. So the second fact was proved by Jason and Yuen.
Yeah.
And then the fact that across an annulus have a lower bound Well, if you think about it, it's kind of clear, but yeah. So that doesn't appear anywhere. I proved that, but it's basically sort of it's basically this work of Jason and Scott and Yuen on sort of on harmonic functions in the mated sort of in these mated CRT maps, and then also you need for that the paper of Jian and Yuen, which basically gives you comparison between graph annuli and like LQG annuli.
Mm-hmm. And you also mentioned that there's something new about the Schneider-Woods, which are like new result. And what's the difference between Schneider-Woods and Uipt?
Well, the reason that say the proof of Tom and Yuen doesn't extend to the Schneider-Woods is just, I mean, they also use this tool of this Markov type tool of constructing of changing the metric, but they do it in sort of they do it in a way that uses more strongly the embedding, and so I guess it's the embedding of the Schneider-Wood into. I don't know if I'm answering the question for you, Yuen, but it's the embedding of the Schneider-Wood into a mated CRT that's slightly deficient.
Yeah. So
did Tom and Yuen cover the case of bipolar orientation?
Yeah, Shin, we didn't do Schneider-Wood because of the technical reason with regard to how the Schneider-Wood case is treated in our strong coupling paper. Because like the way it's done there is like you do the strong coupling with the with like this weighted bipolar map, and then you have the edges to get the Schneider-Wood decorated map. And because of the way that we define our weighting, this version of strong coupling doesn't quite work, right? So you'd have to do you do the strong coupling with the actual Schneider-Wood bijection, and then in a paper with Tom would work in the Schneider-Wood case. But
the advantage of the approach here, I mean, again, I said in the paper that right, it's undoubtedly Tom and Yuen could have altered the proof if they had wanted to do enough work to get it to work. The advantage here is let's see, the advantage here is okay. So this is the that's ugly. Is that sort of this is the assumption that requires a lot about the embedding. I mean, this is the sort of and as you see, this is great. This is like a nice quasi-conformal object. It's about an annuli of two radii that are comparable. So like you don't need It's sort of so in other words, all of the errors that you get from the embeddings, which are polylogarithmic in R, they're easily handled by sort of bounding a quantity like this.
I see. So on top of my head, I think there are some difficulty extending the strong coupling to the Schneider-Wood case that could be suitable for this, because we were thinking of Schneider-Wood as a special case of bipolar orientation, but it's like losing 1/3 of the edges, and if you add in those edges, I think that it's not easy to control the random walk, I guess.
Yeah, I mean the sort of the advantage here of a general theorem was just that sort of like that sort of at least in establishing these exponents, then that sort of distinguish that discrepancy doesn't matter,
Yeah, right.
But it's I mean but to say something about heat kernels, I don't know. Actually, also, I mean, even to talk about Poincare inequalities, I'm not sure that I'm trying to remember. So one can ask, for instance, if a variant of this Poincare inequality is true for, say, for Uipt, or for just a mated CRTs.
I see.
What do you mean by that Poincare inequality?
So it's this thing that's written here, but so it's a little.
So UB
right.
bar is the average over the ball.
Say it again.
So UB bar is the average of U over the ball in this inequality.
Oh yeah, sorry, I didn't write that. It's the average, but here it is the average. But here, let me say it's actually something simpler here. So you could look at this in a different way. Take a ball of radius 100r in Uipt, and then now look at any pair of balls of radius r in that ball of 100r, radius 100r around the root. So any pair of balls of radius r that are separated by constant times r. And now you'd like to say that that between those pair of those balls, the effective resistance is small, r to the little of 1.
Mm-hmm.
So you can do this. Right. Yeah. So that's the point is that if you just want to control the root to the boundary of a ball of radius r, I mean, you know how to do that. You can just use basically you can take a Euclidean flow and pull it back to say the mated CRT, and that will tell you that the effective resistance from the point to the boundary of a ball is small. I'm just saying what you guys do what you do in your paper with Jason. Now things get more complicated. So now of course that also gives that's stronger than having an upper bound, say. So let's see. So basically, I see, right. Yeah, so this is just some kind of directional uniformity. It would suffice to say that from the root to take the root and take any ball of radius r that's within distance constant times r. You would want to say that the effective resistance from the root to that ball is bounded by, polylogarithmic in r. So in other words, you don't get to send flow to the entire. It's basically say that even along wedges you have some control.
Mm-hmm.
Clearly, in the Euclidean case, you can choose a wedge, and then if the wedge is a constant fraction of the circle, you'll get the effective resistance to that arc will be bounded by a constant. Upper bounded by a constant. Upper bounded by like log r. But now, so the point is, so to prove something like the Poincare inequality there, you would want to also have some kind of directional uniformity, which said that sort of, if I take any sort of r ball within 100 r of the root, then I can send a good flow to that r ball. That's a little more difficult. I mean, you can think about it.
So, I mean, I feel like this Poincare inequality is the sort of thing that, like, if it's actually true for mated CRT map, it's probably not too terribly hard to prove.
Unless it's true unless it's true it could be true in a multi-scale way in the sense that there are whenever that sort of like there could be local defects. In other words, it's let's say it this way. To prove the effective resistance is small from the root to the boundary, you just take the sort of the Euclidean, like a flow in Euclidean plane, which is just from the center of a circle, you just take all the lines uniform measure on lines to the boundary, and then you just pull that flow back to the mated CRT.
Yeah.
It seems possible that. I mean, that degenerates in the sense that now if you just choose a flow along a wedge, when you pull it back, the energy could blow up. It certainly, as you take the angle of the wedge narrower and narrower, the energy could blow up as you move back. So in that case, it seems possible that there exists a good flow in the Uipt, like the effective resistance is small, but it's not just lifting the Euclidean flow. I don't know. You see what I'm like? It could. Yeah. I did try to do it. Lifting the Euclidean flow is hard for some reason because you need it seems that you need control on too many events, but I'm not an expert, so I don't know.
I see. So if this Poincare inequality were true for like Uipt or whatever, would it have any interesting implications right away?
I mean, again, if I was to sketch how to prove this heat kernel bound in Uipt, the first thing the first thing I would do is prove a Poincare inequality, and then I think with a Poincare inequality, it should be possible to lift the techniques from analysis on graphs to the case of Uipt. I think that the Poincare inequality is enough of an input to establish this sort of more delicate heat kernel bound.
Okay. So like you think that this Poincare inequality would imply this heat kernel bound that you have on the in like open question 1?
Yes. And the case, at least in the case when zeta is non-negative.
Okay. That's definitely be interesting to look into then.
Right. And like I said, there's two non-trivial components there. One is proving it for, say, Uipt, and then the second one has nothing to do with Uipt. It's proving that the techniques from analysis on graphs that give you kind of heat kernel bounds in the presence of a Poincare inequality and volume doubling, that those would also work in this setting where you have, it's two things, like this setting where you have subpolynomial errors, which is probably fine, but then also in this setting where, like in the recurrent setting, where you don't have these potential theory arguments, and the speed bound comes from a different source. So what I'm saying is that you would have to verify that you can still establish this without some of the tools that they have in analysis on graphs, because, well, without the strongly recurrent tools.
Yeah.
But
in the Poincare inequality, is it okay if the d star is replaced by d star plus a little o of 1? Because I'm pretty sure it's not possible to get it with just a d star there.
Yeah. So that's what I didn't, in order not to make this too complicated, yes. You should do that. Of course, it's not true. Yeah. It won't be true without a correction there. But yeah, that's the. Yeah, the intent is that it should be d star plus the low of 1, and also that 10 r can be replaced by r to the 1 plus the low of 1 as well.
Does anyone else have any questions?
I'm fine.
If not, I have maybe another quick question to ask. So am I right that you don't have any regularity assumptions on the graph, right? Like you don't require any kind of degree bounds or things like that?
Only the regularity assumptions are very weak.
Just like these equalities between exponents, essentially.
Well, no. I mean, there's sort of the existence of the exponents, but like I said, if those don't exist, then you still get inequalities between a bunch of different things. Yeah, these are the. Okay, so like, I mean, if you don't have. So if you want to, yeah, I mean, you need basically, if you start with a unimodular graph, then condition 2 is just that you need the expected degree to be finite.
Mm-hmm.
So you need the expected degree to be finite and sub-exponential growth.
Okay. So it would work for things like these discrete alpha stable maps where you have unbounded face degree. In principle, if you could show the exponents exist for those. And I guess maybe the other sort of example I was thinking of are things like these like square tilings for central charge bigger than 1 Liouville quantum gravity, where you have places where like the faces accumulate.
Yeah, I mean, this should apply there. I think the problem there is that in most cases, like zeta is establishing the existence of zeta of the resistance exponent is tricky. Yeah. I mean, because you don't, yeah. So it should, yeah. I mean, this applies very. I mean, I was fortunate that Gian had this paper. This Biskop Dean Goswami, where they write. I mean, where they're the conductances are crazy, and so sort of, I mean, not crazy, but the point is there that the degrees are. I mean, yeah. There one has quite large fluctuations of the degrees, and so like in order to apply this, I tried to make sure that there was the assumptions on the degrees were as mild as possible, and yeah, and they're very mild.
Yeah. Okay. So I guess if there's no other questions, then I'll just let's thank James for a very nice talk. You can feel free to unmute yourself and clap if you want to, or or not.
Thank you.
Yeah. Thanks for the invitation. That was fun.
Okay. Let's see. So yeah, feel free to stay in chat if you want to, or just go.
So I'm going to have lunch now. So I'll just see you guys. Yeah. But thank you, James.
Yeah, thanks again. Yeah. Oh, actually, I have a meeting, so yeah, I'm going to step off.
Okay.
Yeah, you guys.
Thanks for coming. Very nice talk. Bye.